So 9.2, analyzing rational functions. So we're going to graph and analyze and compare rational functions, which we've done some of before. But now we're going to see a different type of rational function. We'll see whether graphs have asymptotes or points of discontinuities for permissible values. We're going to see that sometimes they'll have one or the other, or sometimes both. So you've worked with asymptotes before. Now we're going to see what a point of discontinuity is. And as it says on the right, a point of discontinuity is a point described by an ordered pair at which the graph of the function is not continuous. Essentially, there's a break in the graph. If you're drawing the graph, you actually have to stop, lift your pen or pencil, move it, and start again. It's one point that the graph is not defined at. Okay, so it's like a hole in the graph. We're going to see that it occurs in a graph of a rational function when it can be simplified by dividing numerator and denominator by a common factor that includes a variable. It results in a single point missing from the graph, which is represented using an open circle. Again, it's sometimes referred to as a hole in the graph. So we've seen that graphs of rational functions have a variety of shapes and different features. Vertical asymptotes are one such feature. So this corresponds to a non-permissible value in the equation of the function, but not all non-permissible values results in vertical asymptotes. Sometimes a non-permissible value instead results in a point of discontinuity. So we're asked to graph that function and analyze its behavior near its non-permissible values. So remember that we've seen examples of rational expressions where the degree of the top was less than the bottom. We did lots of those. And when that happened, the x-axis was an asymptote. Y could never equal 0. Then we saw ones where the degree of the top and bottom were the same. And we saw that the horizontal asymptote could be found by dividing those terms, those initial terms, from those terms that make up the degree. Now in this case, note that the degree of the top is one more than the bottom. Okay, so in this case here, we're going to see what happens when that occurs. And more specifically, in this case, if we factor the top to x minus 2, x minus 3 over x minus 3, we see that we can divide top and bottom by a factor of x minus 3. And you're just left with x minus 2, which is a line. That's a line. It's in slope-intercept form. It has a slope of 1 and a y-intercept of negative 2. However, when you're talking about restrictions, you have to go back to the original expression, which has a denominator of x minus 3. So we would say then that x cannot equal positive 3. Normally, this would mean that you'd have a vertical asymptote there. But however, in this case, by factoring the top and dividing top and bottom by x minus 3, we get rid of that factor. So what does this graph look like? And I will graph this by using the original expression. So the numerator, which I'll put in brackets, is x squared minus 5x. Whoa, try that again. X squared minus 5x plus 6. And I forgot to put that in brackets, so let's do that. And that will be divided by, in brackets, x minus 3. So zoom 6 to set our windows to their standard settings. So like we said, the resulting graph is a line. That is the line y equals x minus 2. It has a y-intercept of negative 2 and a slope of 1. Rise 1, run 1. If we go into our trace mode and we let x equal 3, we said that's a non-permissive value. Look what happens. There is no y value stated. Because again, this is a point of discontinuity. We saw on the previous page that a point of discontinuity occurs when you have a rational expression and you can cancel a factor on the top and the bottom that contains a variable. That's where you get a point of discontinuity from. So again, the calculator won't tell us what the y value is, but we can get that y value from the simplified equation, right? The restriction that x can't equal 3 comes from the original expression. When you simplify it, though, you'll get an answer of x minus 2. But the restriction still holds true. X cannot equal 3. So when we find out what f at 3 is using the simplified expression, 3 minus 2 is 1, that tells us the y value at the point of discontinuity. Our point of discontinuity is at 3, 1. And again, that represents or is represented by a hole in the graph, a break in the graph. The graph of this function will be the same as the graph of x minus 2. Again, that has a y-intercept of negative 2 and a slope of 1, so we can rise 1, run 1, rise 1, run 1. But when we get to the point 3, 1, there is a break in the graph, a hole. But after that, it continues by rising 1 and running 1. So this graph would look something like this. That is the graph of the function. When we put it in our calculator, the original expression, we got a line with a y-intercept of negative 2 and a slope of 1. And even though the calculator didn't show it, there is that break in the graph, our point of discontinuity. Now, if we go back to the calculator, sometimes if you change the graphing mode, so if I go zoom and I choose number 4 in the list, which is zoom decimal, let's see what happens. It actually shows the point of discontinuity. It shows the break in the graph. So it's a different graphing mode. It reduces the windows that are being used to graph, but it also, in this case, shows the point of discontinuity by using zoom decimal. All right, so what does that do to our characteristics? Like, we can state the domain and range of this function. The domain, and if we use interval notation, it would go from negative infinity to positive 3, and then from positive 3 to positive infinity. The range would go from negative infinity to positive 1, and then from positive 1 to positive infinity. And also notice that there is no vertical asymptote here. Our only restriction was that x can't equal 3. But because that factor of x minus 3 canceled out, instead of a vertical asymptote at 3, there's actually a point of discontinuity, a break in the graph. So again, that happens whenever you can cancel a factor on top and bottom, and that factor contains a variable. So we'll do the same thing for this one. We see we have a denominator of x minus 1, so x equals 1 is a non-permissive value. So we're going to see what happens at 1. Is there a vertical asymptote or is there a point of discontinuity? By factoring the top, the factors will be x plus 3, x minus 1, and now because we have a factor of x minus 1 on both top and bottom, we can divide top and bottom by x minus 1, which means now that you'll have a point of discontinuity at x equals 1. It also tells us that our simplified expression is just a linear function, y equals x plus 3. But we have to observe the same restriction from the original. X cannot equal 1. And because x minus 1, that factor canceled, that means that x equals 1, there will be a point of discontinuity at x equals 1. And we can find out what the y value there is by finding f at 1 in the simplified expression. So that will be when y is 4. That will be our point of discontinuity. It'll be the point 1, comma 4. Again, that will represent a hole in the graph, point 1, comma 4. The rest of it is defined by the simplified expression y equals x plus 3. That's a line that has a y-intercept of plus 3 and a slope of 1. We can rise 1, run 1, which will take us to the point of discontinuity. We have room to rise 1 and run 1 2 more times, and we can also rise negative 1 and run negative 1. Negative 1 over negative 1 still gives you positive 1. So all those points will belong to this graph. We just got that point of discontinuity, but the rest of the graph will be a line. Right, and you could check this by putting the original expression in the graphing calculator. It's y equals x squared plus 2x minus 3 divided by x minus 1. When you graph it, I'm still in that zoom decimal mode, and because of the reduced windows, we can't even see the point of discontinuity. Actually, maybe just barely you can see it at the top. If we make our y max a little larger, let's see if that helps. Yeah, now we can see the point of discontinuity clearly. We're still in that zoom decimal mode. Okay? And just to confirm, if you go trace and let x equal 1, no y values return. That confirms that the point of discontinuity is at x equals 1. So let's look at this one. We're asked to compare those two graphs. All that's different is the numerator has a different sign in between the terms. So let's look at f at x first. There is a common factor of x there. Take it out, you'll get x minus 2. On the bottom, I'm going to take out a common factor of negative 2, which will make the 4 negative and the x positive. I should have said not the 4 negative, but the result when you divide 4 by negative 2. So when you take out a common factor of negative 2 on the bottom and just switch the order around to put the x term first, it becomes x minus 2 as well. And so the x minus 2's will cancel. The simplified expression will be x over negative 2, or negative 1/2 x. But we have to state the restrictions from the original expression. And that is that x cannot equal 2. Once again, because the x minus 2 canceled, that means at 2 you're going to have a point of discontinuity. That non-permissive value came from the factor that canceled. So that means you're going to have a point of discontinuity at the point 2, comma, and our y value will be found by letting x equal 2 in the simplified expression. Negative a half times 2 is negative 1. So our point of discontinuity is at the point 2, negative 1. The rest of the graph will be defined by y equals negative 1/2 x. So that's a line that has a slope of negative a half and a y-intercept of 0. Negative 1/2 x is the same as negative a half x plus 0. Y-intercept of 0, rise negative 1, run 2 takes us to the point of discontinuity, but we'll continue to rise negative 1 and run 2. We can also rise positive 1 and run negative 2, rise positive 1 and run negative 2. We can do that as well. So there's our graph. So that's for the graph of f at x. Now we will do g at x. There's a common factor of x on top, which gives us x plus 2. If I take out a common factor of negative 2 on the bottom, again, we'll get x minus 2. The factors don't cancel. They're not the same. So nothing cancels here. We still have the same non-permissive value of x can't equal 2. But now, because that factor x minus 2 didn't cancel, that means you're going to have a vertical asymptote at x equals 2 instead of a point of discontinuity. So we started the lesson today reminding ourselves that when the degree of the top was less than the bottom, you got a asymptote at the or on the x-axis. That was the line y equals 0. When the degree of the top is equal to the one at the bottom, we can divide the coefficients of those two terms to get the horizontal asymptote there. We've said that when the degree of the top is greater than the bottom, sometimes you're going to get a point of discontinuity and therefore no asymptotes. In this case, though, you don't have a point of discontinuity. You have a vertical asymptote. Question is, do we also have a horizontal asymptote? So we will see what's happening by, again, using our graphing calculator. Have to use the original expression. So the numerator is x squared plus 2x divided by, in brackets, 4 minus 2x. When you graph it, I'm going to use Zoom 6 to get my windows back to their standard settings. You actually only see part of the graph right now. You see the left side. There we go, Zoom 6. So what happens here is the graph actually has a slant asymptote. This is something new. It has a slant asymptote. In 30-1, you don't have to know where that slant asymptote is, what its equation is, what it looks like. Okay, it's actually part of the 31 curriculum. So if you were to take calculus at some point, you'd learn about slant asymptotes. So in order to draw its graph, we will just use the graphing calculator and generate some points. Okay, we have a vertical asymptote at x equals 2. So if we go into our trace mode and let x equal 1, we can see that y equals 1.5. So we can put that point on there. The point 1 comma 1.5 is right there. If I let x equal 0, y equals 0. This graph goes through the origin. If I let x equal negative 1, if I let x equal negative 1, y equals 0.16 repeating. So it's positive just below, or excuse me, just above 1. If I let x equal -2, y equals 0. Let me go back. I think that last one was negative, not positive, because I should go through -2, comma 0. So let's check -1 again. Yes, it is negative. So we can move this point just below the x-axis. And when x is -3, y equals positive 0.3, something like that. Let's do one more. -4.6. Right, so that graph would look something like that. Remember, you always need arrows on the ends of each arm of your graph. To the right of the asymptote, if we let x equal 3, we'll get the point 7.5. So 3, 4, 5, 6, 7.5, maybe approximately, or -7.5, I'm sorry. 5, 6, 7.5 is approximately there. If I let x equal 4, y is -6, approximately there. Let x equal 5, it's -5.8. Let x equal 6, it's -6. Approximately right there. And so again, this gives us some points to graph. And it's going to go something like that. So what are the differences? Well, obviously, F has a point of discontinuity, whereas G has both a vertical asymptote and a slant asymptote. All right. So there's really the major differences between those two graphs. So we'll do the same thing for this question. To know whether we have a point of discontinuity or a slant asymptote, we will simplify each expression. So for F, on top there's a common factor of x to take out. On the bottom there's a common factor of 2. X plus 3 and x minus 3 are not the same. They can't cancel. So therefore we're going to have a vertical asymptote. At x equals -3. And because the numerator is a degree higher than the denominator, we're also going to have a slant asymptote there. We will use our graphing calculator again to help us get some points for this graph. So the numerator is x squared minus 3x denominator is 2x plus 6. So x squared minus 3x over 2x plus 6. So we can generate some points here by going into Zoom. I'll start by finding points to the left of the asymptote. Let x equal -4. Whoops, try that again. Let's go to our window. The calculator's froze. So we're waiting for that to wake up. Let's go on and start working with g at x. Again, there's a common factor of x on top. And in this case, the common factor of 2 on the bottom also gives us x plus 3. So those ones will cancel. And so now we're going to have a point of discontinuity. At x equals -3. And our y value will be found by letting x equal -3 in the simplified expression, which is x over 2 or 1/2 x. That'll be 3/2. 3 over 2, or sorry, -3/2. -3 over 2. So, point of discontinuity at -3, -1.5. Once again, the rest of the graph will be defined by the line x over 2 or 1/2 x. So we'll rise 1 and run 2. Rise 1 and run 2. We can also rise -1 and run -2. Rise -1 and run -2. Right, so there's the graph of G. So now we can go back and do F. Which I'm going to have to put in there again. X squared minus 3x divided by 2x plus 6. And now we're going to trace. Let x equal -4. Y equals -14. Approximately right there. Letting x equal -5. We'll get -10. -6. We'll get -9. -7. we'll get negative 8.75. And let's do one more, negative 8. We get negative 8.8. So this is the one arm. Go to the welding lab at 11:15. Welding lab at 11:15. Okay, so on the right side, let's let x equal negative 2, negative 3. Oh, sorry, negative 2. That was right the first time. We get positive 5, negative 1. We get negative 1/4. Zero. We get 0. 1. We get negative 0.25. Let me check this again. Negative 1 is positive 1. There we go. Because positive 1 was negative 0.25. Positive 2, negative 0.2. Positive 3, 0, and so on. So this graph will look something like this. And we can talk about the differences where F has a vertical asymptote at x equals negative 3, whereas G has a point of discontinuity at x equals negative 3. It also has a slant asymptote. So those are the big differences between the two. Example 3, match graphs and equations for rational functions. So we want to match the equation to the appropriate graph. So basically, you look at the graphs. The first graph has 2 vertical asymptotes, which means it's going to have 2 factors on the bottom. The first vertical asymptote is at negative 2, which means x plus 2 has to be a factor on the bottom. Our second vertical asymptote is at x equals 2. So therefore, there'll have to be a vertical factor of x minus 2 on the bottom. That doesn't cancel. Okay, are you with this, Chase? Yeah? Okay, so let's simplify each expression starting with a. There's a common factor of x on top. Take it out, you'll have x plus 2. The bottom is x squared minus 4, which is a difference of squares. It factors to x plus 2, x minus 2. The x plus 2's will cancel, which means that for this graph, you'll have a point of discontinuity at x equals negative 2. Let's just say a point of discont. Just save some room here. At x equals negative 2, we'll also have a vertical asymptote. At x equals positive 2, because we still have that factor remaining. You have to leave? Okay, just make sure you sign out, okay, please? So which graph has a point of discontinuity at -2 and a vertical asymptote at +2? That would be graph 2. Right? The first graph has 2 vertical asymptotes. This third graph doesn't have any vertical asymptotes, doesn't have any points of discontinuity. Only graph 2 has a point of discontinuity at -2 and a vertical asymptote at +2. So there's A at x. B at x. You can factor out a common factor of 2 on top, but the bottom, there's nothing you can do for that. Can't factor it. And also, there won't be any non-permissive values for this because x squared plus 1 can never equal 0. The only way x squared plus 1 would equal 0 is if somehow x squared would equal -1. Then it would cancel with the positive 1, but that's not possible. So there are no restrictions. Our domain for this one will be all real numbers from -infinity to +infinity, which is graph number 3. Graph number 3 doesn't have any restrictions. It goes to the left and right forever. You could certainly put that equation in your calculator, graph it, and you would see it would look the same as graph number 3. So that means equation C has to match with graph 1. Because when you factor the denominator of x squared minus 4, again, it's x plus 2, x minus 2. There are non-permissive values of -2 and +2. Those factors don't cancel, so therefore there's vertical asymptotes at 2 and -2. Which is what graph 1 shows. Okay, so we can do the same thing with this question here. Match each equation to the graph. Graph number 1 has an asymptote at x equals -1, which means x plus 1 has to be a factor on the bottom. That doesn't cancel. It has a point of discontinuity at x equals +1, so x minus 1 will be a factor on the bottom that does cancel. Graph 2 only has a point of discontinuity at x equals 3, so that would have only one factor of x minus 3 on the bottom that would cancel. Graph 3 has two vertical asymptotes at -1 and 2. So x plus 1 will be a factor, x minus 2 will be a factor on the bottom, and neither of those will cancel. So let's look at each equation and see if we can do anything. K, cannot factor the top. You cannot factor sum of squares. The bottom does factor, though. It's x minus 2, x plus 1. Neither of those factors will cancel. So this graph would have two vertical asymptotes, one at 2, one at -1, which is graph 3. Because again, we have vertical asymptotes at x equals 2 and x equals -1, which is what graph 3 has. Right? Looking at equation L. Nothing can be done with the top right now, but the bottom is a difference of squares, x plus 1, x minus 1. So the x minus 1s will cancel. But you still have a factor of x plus 1 on the bottom, which means we'll have a vertical asymptote at x equals -1, and we'll have a point of discontinuity at x equals +1. which is graph number 1. Vertical asymptote at -1, point of discontinuity at +1. And so that leaves graph 2 for equation M, which means we should only have a factor of x minus 3 on the bottom. So let's see how this works. We can factor the top to x minus 2, x minus 3. And to get an x minus 3 in the bottom, we would take out a common factor of -1. So the x minus 3's cancel. And because that factor cancels, that means you'll have a point of discontinuity. At x equals 3, there's no vertical asymptotes. Because there's no more factors left on the bottom that contain the variable, which again matches graph 2. So on page 452, you can do questions 4 through 6. You're going to hand this one in for marks. Okay. Some of you have been complaining that you haven't had enough homework assignments to hand in, so today's your lucky day. Julia, you've been complaining hard.